Hi there everyone, welcome to the video lecture series of eigenvalues and eigenvectors. I'm Mayur Gohil, and in this video lecture we will be discussing a new topic, a very small and easy topic but a very important one which will help us to determine some new concepts also. So let us see one small result which will help us. The result is, if A is a triangular matrix, then its eigenvalues are its diagonal entries. Now this is one of the first results based on the type of a matrix, and we are able to find the eigenvalues. So either A is upper triangular or lower triangular matrix, then its eigenvalues are its diagonal entries. Remember this result, we will soon use it. Okay. Now the core concept of the video lecture, we are interested in finding the algebraic multiplicity and geometric multiplicity, for which the definition are as follows. Let A n cross n be a square matrix. Since it is a matrix of order n, we assume that there are lambda 1, lambda 2, lambda n eigenvalues. Okay. So there are n eigenvalues. Then suppose lambda 1 is repeated k times. Okay. Then k is said to be the algebraic multiplicity of lambda 1. Okay. So the algebraic multiplicity of a particular eigenvalue, say lambda 1, is nothing but the number of times it is repeated. Okay. So now let us go for the geometric multiplicity definition. This definition is slightly non-trivial, but it's important. If R is the rank of the matrix A minus lambda I for a particular lambda, then n minus R is the geometric multiplicity of that particular eigenvalue lambda. So this definition of geometric multiplicity, I'll help you with an example. Also, we will see an example for algebraic multiplicity first. So, let us take this example. We say we have to find algebraic multiplicity and geometric multiplicity for this matrix A. So, for which we will first need to find the eigenvalues. If you observe this matrix A, it is a triangular matrix, and it is an upper triangular matrix, right? So if you use this result, it is nothing but telling us that the eigenvalues are its diagonal entries. So you can immediately write it that since A is a upper triangular matrix, its eigenvalues are going to be lambda equal to 2, 1, minus 1. Straightforward, nothing else. Okay. Now let us first focus on what is algebraic multiplicity. Algebraic multiplicity, remember that you calculate it for every eigenvalue. It is not for all the eigenvalues at one and the same time. It is for each eigenvalue you have to individually calculate. So lambda 1, over here lambda 1 is 2. So lambda 1 equal to 2. So it is repeated only one time. So algebraic multiplicity of lambda 1 equal to 2 is 1. Since it is repeated only once. Similarly, for eigenvalue lambda 2 equal to 1, it is again 1 because 1 is also repeated one time. Similarly, for lambda 3 equal to minus 1, it is 1. Okay. Try for this matrix B. It is again a triangular matrix, but now it is a lower triangular matrix. Again, the eigenvalues for this are going to be the diagonal entries, that is 4, 7 and 7 are going to be the eigenvalues. Let us now try to go for the algebraic multiplicity. Algebraic multiplicity for lambda 1 equal to 4 is going to be 1, because 4 is just repeated once. What about 7? I see it is repeated twice. Okay, so algebraic multiplicity lambda of lambda 2 equal to 7 is going to be 2. Okay, now this is what I mean by algebraic multiplicity. I am now going to focus on geometric multiplicity. Let us try to understand the definition again once more. If A is an n cross n square matrix, lambda 1, lambda 2, lambda n be its eigenvalues. If R is the rank of the matrix A minus lambda I, n cross n, okay, this is the n cross n matrix, for a particular lambda, then n minus r is the geometric multiplicity of that particular eigenvalue lambda. So first of all you need n, which is already available from the order of the matrix. We need to find r, of which r is the rank of the matrix A minus lambda I, for which we will need lambda. So let us try to understand with the help of an example. Consider this very small 2 cross 2 matrix. I am writing this statement because this is our basic statement, how we started our concept of eigenvalue, that is A n cross n into x, which is an n cross 1 matrix, it's a column vector or a column matrix, times equal to lambda times n cross 1, which is where x is a non-zero vector. Then this implies that determinant A minus lambda I is equals to 0. That is our characteristic equation. Now in order to find determinant A minus lambda I equals to 0, either we use the characteristic equation formula, or you can just directly write the characteristic equation over here, that is lambda square minus 5 lambda plus 6 equals to 0. Remember, it's lambda square minus the trace plus the determinant, right? So that is equal to 0. Now simplify this quadratic equation, you get these factors, lambda minus 3 times lambda minus 2 equal to 0, and lambda is equals to 3 and 2. And the algebraic multiplicity of 3 is 1, and algebraic multiplicity of 2 is also 1. Okay, so we are done over here. Now let us go further. Consider lambda 1 equal to 3. For lambda 1 equal to 3, we want to find this matrix A minus lambda I. So that means A minus 3i x, right? A minus 3i x equals to 0. How do I get this? You substitute this 3 in this equation, okay, and when you write this A x equals to 3x, take 3x onto the left hand side and take x common from the right hand side, okay, because it's a matrix operation, you have to remember to take it from left hand and right hand side, everything has to be properly written. Okay, now we have A minus 3i x equals to 0. So basically when you substitute the matrix over here, what you will get is 4, 5, minus 4, minus 5, and this x will be nothing but a unknown vector, which is a column vector, because it's a n row and 1 column vector. So n rows, because here it is a 2 cross 2 matrix, so it will be 2 rows and 1 column. Okay, now this is the system of the linear equation. You want to now find the rank of this matrix A minus 3i. So A minus 3i rank can be found using row echelon method. Okay, you reduce this matrix to row echelon form. using the following row transformation. First perform R1 changing to R1 divided by 4 and R2 changing to R2 divided by 5. And after having those transformation performed, you then perform R2 changing to R2 minus R1. Finally, you will obtain this matrix, that is 1 0 minus 1 0. Okay, so if you observe this 2 cross 2 matrix, it is nothing but a row echelon form of the matrix. In row echelon form, if you remember in my first video lecture, I told you that row echelon form of the matrix gives the rank of the matrix. That is, the number of non-zero rows in the row echelon form is nothing but the rank of that matrix. So here there is only one row which is non-zero. So the rank of A minus 3i is nothing but 1. Okay, because there is a one non-zero row. So rank of A minus 3i is 1. So we have found R. Okay, now let us try to find the geometric multiplicity. N is equal to 2. Okay, N is 2 because it is the order of the matrix. Done. So now to find geometric multiplicity, we needed N and we needed R. We have both of the terms. So finally, geometric multiplicity of eigenvalue lambda 1 equal to 3 is nothing but N minus R, which is N is 2 and R is 1, which is equals to 2 minus 1 is 1. That's it. So geometric multiplicity is 1 for lambda 1 equal to 3. So similarly, try finding out the geometric multiplicity of eigenvalue lambda 2 equal to 2. Okay, answer is going to be 1. I'll tell you how. You just have to plug up over here in the same fashion. For this equation, instead of finding A minus 3i, now find A minus 2i into x equal to 0. Reduce it to row echelon form. You will get the rank of A minus 2i. Then N is already fixed, which is 2 because the matrix order is 2. And then plug it up in the formula, you will get the answer. This is the concept of geometric multiplicity. So I will deal with the other advanced topics in my other video lectures. Till then, keep solving good problems on mathematics. Thank you.